this assessment, we're asked to predict the product of the reaction shown. The reaction shows a ketone reacting with DCl and D2O. The D represents deuterium, an isotope of hydrogen. And so as we think about the reactivity of this, we can pretend that D is H, in which case we can think of this as if it were HCl and H2O. We're just using the isotope. Now DCl and D2O are going to combine to give D3O+, which we can draw this way. D3O+ is acidic, and in the presence of acid, this ketone can equilibrate to give an enol. Now the enol won't be the favored side of the equilibrium, but we can make this enol. And now because there's deuterium in solution, we're going to put the D as the group of the enol. Again, this would look just like an enol if this were an H. D does exactly what H does, so this is our deuterated enol. From here, we can think about the mechanism of the next step, that this acidic proton can react with this alkene by using this lone pair to come down, push those pi electrons out to protonate, to grab this deuterium, in the same way that it would react with H+. What that's going to give you is the incorporation of one deuterium atom. At this point, we can remove, using D2O, we can remove that proton, that deuterium, from the ketone to give us the ketone with a single deuterium incorporated. Now, while we've shown mechanistically how we incorporate one deuterium, the reaction can happen again. We can make an enol, removing the proton that's here. We can make an enol again, removing the proton here, and we can replace each of them with deuterium. So this same process can happen 3 more times until eventually we've replaced all of the enolic hydrogens with deuteriums. Now you might ask the question, what about these hydrogens that are here? Because those can't be involved in enol formation because they are not alpha to the carbonyl, these hydrogens remain untouched. We can only add deuterium to the so-called alpha carbons.